Yeah, okay. So let us continue. Um, so in general, we have a numerical controlled machines. These are machines with a few degree of freedom, just not like unlike robots. They have some limited degree of freedom most of the time. There is either a rotating tool or a moving tool, a linearly moving or a rotational tool, or there is a linearly moving workpiece or object or a rotating object, you know. So we have a tool. It is a process of maybe material removal, you know, just maybe this is some sort of subtraction manufacturing, or it could be also additive manufacturing, like in additive in 3D printing. You follow some axis motion, you know, you have, for example, 3-axis motion, and these axis motions will build one on the other and then create a product, right, at the final. Or there are other machine tools like milling machines, where you have subtraction of materials, you know, from the given stock or workpiece, and then finally you will have a final product just by removing some sort of materials by some defined material removal rate. So it is either for subtraction, or it could be also for addition manufacturing, or it could be also other. So these are machine tools with a limited axis, but with some potential advantage, like stiffness, accuracy, mass productivity, and so on. You know, these such types of machines, numerical control machines, could have better advantage than robots, because they are useful for heavy operations where you have high load, where you have high stiffness, where you have high accuracy, and also where you have high production rate. So for the matter, just we have a standard machine language, which we call it G code. And these G codes are used to standardize how numerical machines are going to be controlled. And just they are following the standard, given by DIN 66025 or ISO equivalent, which is generated by International Standards Organization of Electronic Industries Association, EIA. These guys are responsible for this such type of code generation. So according to DIN 66025, there are block numbers which describe the sequence of operation, which is termed as N here, which is N. Or there is a machine command, a machine command, which is described by 3 variables. For example, like G is a machine function. Okay, it is a function to do something. For example, G00 is rapid positioning, G01 is linear movement, G02 is circular movement, and the G03 is also a circular movement with counterclockwise. So these guys are used to define some preparatory functions, or also we could call them preparatory functions. These G codes, they are used to command some operations for the machine tool. Then the other is, there is some command called T, just which we use it for tools. Just we say tool number 1, tool number 2, tool number 3. You assume you have multiple tools for different processes. So for example, maybe for rough cutting, maybe you need some different tool, and maybe for surface finishing, you know, for smoothing, you know, you may need different tools. So these tools could be identified by their tool number, tool 01, 2, 3, 4, 5, 6, and then accordingly the machine will exchange the tool and then perform the operation. Then the other is M functions. M functions are called miscellaneous functions, and they are a command for operations like start motor, stop motor, coolant on, coolant off, and so on. Okay, so for example, M30 is end of the program, M03 is to start the motor, and so on, something, M05, M07, 09, something. So these are the commands. The other is actually you have also some denotations for axes. For example, XYZ is main axis, and ABC is a rotational axis. Okay, ABC is a rotational axis along XYZ. Just this. Then also there is if you have the second movement, you know, you can use also UVW. If you have again third movement, you can use also PQR, and so on. So yes, this is the standard. Actually, also if you have some geometries like circular, you may need maybe IJK, and so on. So S is spindle speed, and T is tool number, G is preparatory function, and N is a sequence number. Yes, then F is feed rate. F is feed rate, and yeah, if you have multiple axes, then maybe you could use additional feed rates with ED something. Yeah, something like this could be used here. So in general, CNC machines are executed by NEC programs. You know, they are executed by NEC programs or part programs, and these part programs could be written by following the ASCII format. Just so you may put this into CD or maybe flash disk or USB or something, and then put it into the machine and then run on the machine system. As you see it, just the machine system could be something which looks like this, where you could program your your product just from the interfaces. You could read it here, your data, and then follow it, also monitor it on real time. So in general, whenever you consider such machine tools, you could expect components like there's a mechanical component regarding the hardware. There is a component for power units, which has motors and amplifiers. And then there's also a CNC unit, which is a central processing unit with input and output devices, logical controllers, and interface devices. So yeah, just as any robot, or maybe as any computer controlled machine systems, you expect something like that. So this is what we have there. Now, there's one important point, actually, whenever you have these machine tools, okay? So these machine tools could be, you know, it could be a lot of variety. For example, as you see it here, there were evolution. In 1797, it was very too manual. In 1906, also a little bit automated, and so on and so on. Now, nowadays, we have really really advanced machine tools. Yeah, in these machine tools, actually, we have some conventions. These conventions, you know, according to the DIN 66025, we mentioned here. there is the axis denotation, and this axis denotation says you have to assign x-axis. Maybe we start from z-axis. Z-axis, you know, as we had been talking in the robotics lesson, z-axis is always along the axis of rotation. This is again true for numerical control machines. So what is the rotating axis? So if you have a rotating axis, it could be a rotating axis of the workpiece also, because when the tool, sometimes like in CNC machines, in lathe machines, there is a workpiece which rotates, and there is a stationary tool. Of course, not stationary tool, but a linearly moving tool. So this time, the z-axis we assign along the axis of the object rotation, or of axis of the workpiece. For example, here on this machine, you have this guy. Let me check if I have something to. Yeah, so let's say you have this is an object which is rotating. Along this, you have axis which is assigned along z-axis. Here, you have this, say, let's say this is z, and then you expect the second one. Do we say it with green? No, this is red actually. This is red. Okay, then don't I make another one? No. Okay, then the other is okay, so let's say this is y-axis. This is y-axis. Then there is the third axis, which is along the axis of the linear movement of the tool, which is z. Maybe which we said this is x-axis, y-axis, z-axis. Yeah, so this time the axis of x is always along the tool movement, which is a linear movement, okay, in this case. And then we have z-axis, which is rotational, which is along the axis of the object. For example, look at this example. Okay, for this example, you have z-axis, which is moving along this axis because the object is rotatory. The object was rotatory. So since the object is rotating, you have z-axis along the axis of rotation. Then the x-axis, this x-axis was represented along what? X-axis was represented along the tool axis. This is tool, okay? This is tool. Along this axis, there is a rotation. This is, there's a translation. So here there is a translation, which is a linear movement. And here you have a rotation about z-axis, which is a revolute movement. So it is a rotational movement here. We have here translational movement. So because of that, we follow z-axis along the axis of rotation. This is along axis of rotation. And we use x-axis along the axis of a linear movement, or along, if you don't have a linear movement, along the longer axis, just we take it along the longer, and then y is right hand rule. Just follow the right hand rule, then it will be fine. Okay. So this is one thing here. We want to know, at least here. At least we have to know it. Okay, now I would like to go to the next step. This is actually for turning operation. It is for turning operation. Turning operation is most of the time done by the lathe machines. I hope you know this turning machines. Maybe if there is someone who doesn't know. Axis, and this is moving along this axis. In the same time, at the same time, this tool is also moving in this direction, to this direction, you know. This direction is called feed. You know, it is feed movement. And this direction movement is called longitudinal movement, or it is removal. It is a process of it is cutting, you know. This time it is cutting, or it is removing parts. Okay, it's removing some materials from the workpiece or from the object, so in order to bring into the final shape, right? So so just here you have automated system, you know. Nowadays in numerically controlled machines, the movement of this tool along the radial and longitudinal movement is controlled by the numerically controlled controller, by your controller. And the rotation of the tool, the workpiece here, the rotation of this workpiece is controlled by the movement of the spindle, which we define it with the spindle speed m. Okay, we say m, sir. You know, sorry, with a speed s. Okay, we say speed is 1000 rpm, revolution per minute, or 2000 revolution per minute, 2000 revolution per minute, maybe 5000 revolution per minute. I don't know. Just it's where you define this RPM. Yeah, actually decides the movement of the workpiece, and the feed rate and depth of cut will decide how far you should move toward the object with the depth of cut, and feed rate is how much material you have to remove per second. Okay, just how much materials you have to remove per second. Then also you could have a possibility to calculate a material removal rate. Material removal rate is a volume of materials removed in a second, you know, in a given time. So this is a volume of materials to be removed. So you have to calculate the volume over time. It's a material removal rate, and distance of depth over time could be a feed rate, and so on. Okay, so you can calculate some variables like that. Okay, so now yeah, I think this much should be enough. Then this is lathe. Okay, in lathe machines we are having a rotating object or workpiece and a linearly moving or a translating tool. Very important. Okay, the next is some operations like milling operation or drilling operation. Now, reversely, there is a rotating tool and a translating object. So the tool is rotating while the object is either stationary, it could be also stationary or linearly translating. The tool could be also rotating, also it could also simultaneously translate, you know. For example, you have a fixed workpiece here, you fixed your workpiece here, and you fix your workpiece here, and you want to create this hollow. Just here we want to remove this section. So what you have to do is rotate your workpiece, just linearly move down, move here, then move here, move here, move here, and then finally you are done, right? So if you want to do something like this, then it is a linearly moving motion. So translating down, then translating here, then just make something like this, and then finally you will be done. So while the tool is rotating, it is also doing translation. There are some options where the operations where the tool is only rotating, but the workpiece is moving. So yeah, so you could imagine drilling operation, for example, milling operation, and other factors. Actually, as I have to repeat it again, the axis of rotation of the tool is always assigned for z-axis because of the rotation of the axis, and the longer one will be assigned for x-axis, the shorter one will be assigned for y-axis. The same thing, you know, whenever we do these operations, sometimes assume you are operating, you are cutting a turbine blade, okay? Turbine blade or pump impellers, you know, this pump impeller blades. So maybe, I don't know if we could have something like that. Maybe we check it on YouTube. Because in such operations, you have very, very complex geometry, and to perform this complex geometry, you need yeah, very nice, yeah, maybe a very good tool pass plans, and this time these tool passes are really not easy. Yeah, actually, this is a impeller pump, for example, and what the guy was doing is he has to create, you know, this is really a complex geometry, very complex geometry, and he has to do all this operation. So each time, you know, each time it has to, yeah, perform, you know, the tool is rotating as well as linearly moving, you know, and now he has to do so many operations. First is just do some rough operation with large depths of cut, and then finally he has to do a finishing operation with small depths of cut, but with high speed in order to make the surface very smooth, so that you will know, you will avoid yeah, a possible friction, you know, when the water hits the surface, and it will not make any loss of energy. Yeah, so this is it, and then I hope you will see finally you will have a shape, something which looks like this. It is really yeah, it's really a complex geometry. It's a really complex geometry, and it may take a lot of time actually just even to complete. Here it is putting some coolant. Coolant is just for absorbing a disseminated heat, because if it is especially steel, it generates a lot of temperature heat. So this heat should have to be absorbed, just also has to be avoided. So now look at then finally what it looks like. It's really look, it's really amazing. It's really amazing. Yeah, it is really a very complex shape. So in order to produce such objects, you need thousands, maybe millions of lines of codes, right? Maybe millions of lines of code. And you need also different tool types. You know, you have different tool types. you have different speeds, you have different also configuration, you know, how you have to place the object, and also the tool could be also something strange. So in such situation, actually, how we have to assign our reference frame is just we take, at one point, we need to assign a global reference frame where we say we have z-axis aligned along the tool axis, x-axis and the y-axis maybe along the horizontal plane, and then the surface, this complex surface will be then have its local reference frame with respect to the global. So this is your global reference frame. Then for each point, you have different reference frames, right? It is a moving reference frame. You have a moving reference frame, but that will be calculated relative to the global reference frame, and then it's okay. Now, actually, as I said, there are so many there are so many machines. For example, here, as I said, you have a 3-axis drilling operation. So you assign z-axis along this, y-axis along this, x-axis along this. For example, here you have gantry machine systems. Gantry is where all axes are translating, and in this situation, you have to assign along the motor axis here, where you have the tool, at least x-axis, z-axis, sorry, and you have to assign the longer one with x-axis and the shorter one with y-axis. Actually, there are other complex machine tools like this with lots of degree of freedom. Just it has at least 5 axes. In 5 axes, as I said, just we apply the same thing. The axis of the tool we consider it as Z. The longer axis we consider it X. The shorter axis we consider it Y. Again, for this tool only, we have an additional axis, which we call it W. We have a rotation axis here, which we call it C. We have a rotation axis, which we call it B. Yeah, this is for when you have multiple axes. Now, the question is, how do we write this? How do these machines interpret these parts programs or syntaxes of machine language? So this machine language, which we call it G code in numerical control machines, it could be written in block, which looks something like this. So this means literally just this is number of sequence. This is the 40th line, G91 incremental positioning. X is 25, Y is 10, Z is minus 12.55, feed rate is 150, delta speed is 110,000, 1100. Then tool number 6, start motor, maybe coolant on, I don't know, M07, I forgot actually, but we will see it later. Yeah, coolant on, M07 is coolant on. Then this way you have this complete code. Then the machine says, okay, this is go to number 40, apply incremental positioning, then put the X along 25, Y along 10, Z on 12.5, minus F in 150, so on. This is a syntax. And now just our today's main topic is to interpret these things. So how does the machine know this? You know, this is some magic formula, but how does the machine interpret this? Is something which is interesting really for us. So as I said, maybe you don't have to really know everything. but you have to know some of the basics. The basics is G00, G01, G02, and 03, CW and the CCW of circular motion. G01 is linear motion. It is the tool path velocity is kept constant at the given feed along the indicated straight line. This point-to-point rapid positioning is, yeah, it uses the maximum speed as much as possible, and it has low, yeah, it has maximum force, no, maximum speed, but minimum force. So you don't have to expect any force here. Then the other thing that you have to know is if you have cornering, if you have to do a precise cornering, and the other is if you have to do 41 to 42 cutter compensation. And the other code that you have to know is if whether you have to use incremental or absolute positioning. And the other thing you have to know is either M00 or M30, end of the program, on the stopping. Then I would suggest you know also M03 or 04. Then also you know M05, M06, M07, and 08. I would say remember it by heart, these codes that I marked, okay? Maybe G71 for metric units, it doesn't hurt to know, optional. 94, 95 also doesn't hurt, just optional. So, but mandatory. This is mandatory, this is mandatory. You have to remember by heart, by heart. This also by heart, this by heart, by heart. Memorize by heart, this one also. And by heart, by heart, by heart. You have to know. Okay, so now maybe you are wondering what is incremental, what is absolute, what is cutter compensation, and so on. Maybe you are wondering what are these guys? What do we mean by cutter compensation, by incremental or something? Absolute means you have one absolute axis. From the absolute axis, you have absolute positioning. You know, if you have 2 pointers here, maybe point A and the point B, you know, we can say this A, we could say this point A has a distance from this, and we could say this B has a distance from this. You know, this is absolute. But if you measure distance of B from A, it is incremental. This is incremental. This is absolute. Because of the global. With respect to global, with respect to local point. Now you have these points, okay? You want to connect a line through this to make a path. If you have this delta in between, this is here is x naught plus delta gives you here. From here, x1 plus delta gives you here. If x1 plus delta, it gives you here. X plus delta gives you here. So this is incremental. Absolute is you have this distance 5. From 0, it is 5. Here is 10. Here is 20. Here is 30. Here is 40. Here is 50. This is absolute. Nothing else. It's nothing magic. The other is a compensator. The tool compensator means when you have a billing operation, you have a tool which has some radius. You know, the tool itself is circular and it has radius. So this time the tool if you want to cut the operation, you know, if you want to make some operations, then, for example, assume you want to make something like this. Maybe if you want something to make something like this, yeah, you know, there has to be some distance between the tool and the workpiece, you know, there has to be some distance. So this time your cutter has to follow through this path, you know, without touching the corner. So that means this is circle, this is circle, this is circle, okay? So this means the tool radius was compensated, you know, as you see it here. You know, in order to cut at this this edge, you have to move, you have to have offset of the radius of the tool, which you have to let the machine to automatically consider to compensate your tool, or you have to program it. Either you have to program it, you know, you have to add on your pass pointers, or ask the machine to consider a tool compensation. Okay, so by this time you could avoid any mistake, you know, any error, because you could, yeah, make some error. So this is what we call a tool cutter compensation, which is 41 and the 42. Actually, even the compensation could be, is it from the right side or is it from the left side? That's also very important, you know, how does the operation looks like? If it has to be from the right side, consider the right side tool compensation. If it is from the left side, consider the left side tool compensation. That is something really important. Yeah, the other is actually whenever we talk about this rapid positioning, okay, that's the three things that is very important for us. The others are, yeah, the others are not that much difficult. The difficult parts are these three guys: G00, G01, and the 02, or 003. Actually, they follow the same thing. Now for 00, rapid positioning means, you know, I don't know, just I will say, maybe just, you know, for example, if you have this P2 equals to P1 plus delta, you know, it is plus delta. Delta is the distance between P1 and the P2, right? Delta means where delta is P2 minus P1. Okay, so this is rapid positioning. Come, boom. But it is a machine, you know, machine needs some time and some speed, you know. So this time we have a velocity. Velocity equals to distance divided by time, right? Distance divided by time. So your distance is actually, now the distance could be delta, then delta, then time. You need a time. So how fast should it move? So I will say for rapid positioning, okay, when it is G00, it has to use a maximum velocity. V is velocity, maybe I would use abbreviation. V equals to V max of the machine, you know, the maximum velocity of the machine. The distance is actually known. What is not known is what is, yeah, is a time, okay? The time is, this is maximum time of the machine, okay? From the machine spec, you get it. Then you have a time, so the time will calculate at 0, this here, at 1, here, at 3, here, at 4, here, at 5, here, at 6, here, at 7, here, at 10, here, at last, here. So it will, yeah, achieve the distance. So this is with a maximum speed and so on, nothing fancy. But it comes to require a speed adjustment or adaptation when you have to talk about G01. So in situation of G01, the same thing, but the velocity is not the maximum velocity, you know. It is not the maximum velocity, but it is a controlled velocity, okay? It has to be a controlled velocity. So this time P2 is the same thing, P1 plus delta, but this delta is velocity times time, right? This is, but if we have to talk, you know, in a very discrete pattern, I mean, if you cut it, if you discretize it into pointers, you know, like this, then you have to talk about these smaller things, you know, about this infinite small notations. I hope you know it. For example, let's say P2, P1 is at the global. Maybe just let's talk about X and Y. So this means, you know, if for X axis, okay, X2 equals to X1 plus integral of V times dt, right? You know, when we have into small numbers, you know, we have to integrate it over, and then the y2 equals to y1 plus integration of v dt. But here this is vy actually, and this is vx. Okay, just we have to do something like that, right? Now, if we say, just still, if we go further, you know, if we don't want to make it an integration, if we want to have a numerical, actually, you know, if we want to make it in discrete event, then maybe we want to make x2 equals to x1 plus delta x, and y2 equals to y1 plus delta y. You know, again, if we want to make just more generic, you know, if we want to make more generic, between the P1 and the P2, we will divide into number of elements. This number of elements could be maybe 1,000 or 2,000, I don't know, just depending on the precision of the measurement. If your measurement is about 0.01, you know, maybe you have 100, maybe 1,000, maybe depending on the distance as well. So this division could be, you know, we could assign it with n. N is not the n of the other guy, you know. N, in the other time we have n for sequence number, but here it is number of samples. It is number of samples between samples between start and end point. Between the start and end point. Between the start and the end point, there is a sample. So between P1 and the P2, I assume we have example, we have 1,000. Okay, boom, 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 boom. So 1,000 times. The machine should have to make 1,000 times as speed adaptation. So to do that, yeah, now with this concept, actually, we can rewrite this one as generic, maybe for example, like we can rewrite this generically as x equals to x2 equals to x1 now assume initially it is 0, here it is 0, here it is 0, then 1 2 3 dot n. Here n minus 1, here not here n minus 2, here n minus 3, here 0. So n now if we follow, you know, this incremental x1 x2 equals to x1 delta x, right? Delta x. X 5 equals to x, maybe just let's say x3 equals to x2 delta x. Then continue. Then x n equals to x of n equals to x n minus 1 plus delta x. Now, could you imagine a different way of writing this? I could imagine x of n equals to x1 plus something delta. What is this something? I need your feedback. Another way of alternative. Yeah, what is question mark? Anyone listening?
One.
Maybe Abdullah?
I'm just trying to understand it. Maybe I'm wrong. This one.
Maybe Pavan, do you have something?
So 1.
1
n minus 2.
n minus 2. Okay, so let us look at now. X2 means x1 times delta x. X3 means x1 plus 2 of delta x. X4 equals to x1 plus 3 of delta x, something. Maybe I will imagine x minus 1, n minus 1. What do you think? I mean, just you have to do something, some calculation here, you know. For example, just do some simultaneous. Solve for example here, substitute x2, you know, substitute this one. Now substitute this, copy and substitute it here. It is x1 plus twice of delta x. Now assume the third one, which is x4, which is x4 means x3. X4 means x3 plus delta x, right? Now I will copy this one and paste it here. Now it is 3 delta x. So xn equals to x1 plus, if it is n, this is x1, then this is n minus 1. So this is generic. Now this is generic when it is here, 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 here. And then I will make this one also for y. Now, just to be more generic now, I will generate my equation here. And then say, okay, xn equals to x1 plus n minus 1 delta x, and then you need for y-axis as well. Y-axis is nothing else, the same thing. Y. What is delta? What is delta now? Delta is the smallest distance between these guys. You know, it is between this is delta. This is delta. Okay, that is delta. Yeah, good. So this is delta. You know delta. Delta is P2 minus P1 divided by number of samples. Okay, so now let's continue. Now this, so with this, you could directly program your G1, G01. And the only thing missing here is velocity component. We will talk about velocity next. Now, but first, let us see for circular. For circular, nothing else actually. Just the only difference is you have a center, right? Center of circle. So for this, you have to apply circular equations where you say circle is, as everyone knows, right? X minus xc the power square plus y minus yc the power square gives radius. This is just an elementary circular equation. So with this equation, you know, what we have to do is we have to find discrete pointers. We have to cut this one into, discretize into number of elements like this, and then interpolate between the starting and the final point, and then say, where is it now? You know, you have something like this, and then you have to let the machine seamlessly operate. Something like this, nothing else, you know. So the trick is, if you know the circular equation, motion for circular equation is actually, the G code is given by like something like this. This is absolute, this is counterclockwise rotation, X value, Y value, and radius, and feed rate. So what we need is this, guys. We need X component, Y component, and radius. Or there's another option. instead of radius, you can use the center of the circle. I and j is the center of the circle, x position, y position, center of the circle. This is the second option. Either you represent by center or you represent it by radius. Both are possible. But the center of the circle means, I mean, if you represent with the center with ij, this I represents x minus x, center of x minus initial, j is center of y minus initial. This is to have an offset because, you know, this circle has an offset, okay, from this. You know, this circle center has an offset, so you have to get the offset. You have to get the offset and this. So this has an offset, so this offset has some offset from this, so you have to get this offset. Yeah. Yeah, that's why we need to calculate that. Then the other point actually is
Mr. Turik, can you come back, take a picture? Thank you. One moment.
Where?
Previous page. Yeah. One moment. Thank you.
Okay. Yeah, the other point is how to make this circular equation. Okay, how to make this circular equation. This circular equation, yeah, it's really not really difficult. You know, what you have to do is just, for example, let's start. Now we need x position and the y position, right? Just we need x position and the y position. So for this point, we need x position and we need y position. Then if you have this second point here, you need x position, you need y position. If you have third point here, you need x position and y position. When you are here, you need y position and x position. Now, let's say this is 0, 1, 2, 3, and then finally at fourth you are there. Okay, so now let us do as we did earlier. So let us let us do the same thing. X 1 equals to x naught plus radius cos theta cos delta maybe cos theta. I don't know, maybe why not, maybe delta y, cos delta theta. Okay, cos delta theta, maybe why not. Then I will go to the second point, x2 equals to x1 plus r cosine delta theta. Just I will talk about this. Then maybe I will say, just maybe I'm really curious, and then maybe I will say xn equals to x1 plus r cos r cos n minus 1 delta theta. Maybe, I don't know, maybe you like it, maybe you don't like it. Just let me put my proposal, okay, like this. Just now, I think it could work like this. Maybe I will talk why I would suggest this. maybe no, maybe actually this is not 1, but it is x naught, sorry. No, this is x1, sorry, x1. Yeah, sure. Maybe this is x naught, x, maybe this is maybe this is not right. Maybe I have to make this one x naught. I think this way, x1, x naught, x2, x1, x naught are, I think it should work like this. Okay, now why do I say x naught r cos? Do you understand why I say why I took r cos theta? Anyone? Anyone who understood this? I have some reward. Okay, so I will answer it myself. Okay, so that's why I say this r cos theta is, you know, here maybe I have to remove this guy. Okay, so now maybe this also not worse, it does worse. This does worse also. This does worse. Okay, so maybe now you will check. Just follow me. Now, this is 0. This is 1. This is 2. This is 3. This is n. Okay, and now we did it. Then we cut this into this, and then finally this. Now we have, because it is circular, right? So for this one, I have to decompose it into x axis and the y axis with this radius. So it is, this is RC cos theta is, if I have theta here, okay, is along x axis, and R sin theta is along y axis. The same thing for this, I have these smaller distances, okay? So these smaller distances will produce a very small theta, which is delta, which is delta theta, okay? Which is delta theta. So the same is true. So now here, this is for our x-axis. For the yn, it will become y naught plus r sine n minus 1 delta theta. It will work something like this. So this is for circular motion, which is G0, 2 or 0, 3. Now let us look at the exercises from this. This is a demonstration actually that I had been talking. This is about if you want to use existing tools like SolidWorks, you can directly just do it. It is easy, and it will make visualize it. It's for cutting and then just generate the codes and so on. Or if you want to have some custom my generation, actually I have one paper here where I try to generate with MATLAB the codes. Just if you are interested, you can look at. This is what I was this is simply for you to understand, you know, you don't have to about this topic. I mean about the vectors and the lines. This is a revision, okay? So it is a geometry algebra class, so you don't have to worry about it. I don't expect you even to read it, but I have to revise it for you because it's important. So now here, what is important for us is, so now what we had been talking is about these interpolation methods. Here we have, this is what we talked earlier. And this is what we derive, and this is how we say the feed rate is, how the velocity is calculated. It is the delta x over time. And this is what we calculated. And then finally we get to this point, right? We say the current position is the starting point plus k delta x. Just the same thing. So it is delta x times the current point, or which we call it, it is xk, it is x into k minus 1. K is actually what we said n before. It is delta x. This is the same thing. This is a simple function in Python. Actually, I've implemented. Just if you want, you can simulate it. You can try out. Just yeah, then it will generate something like this for you. Then for the circular interpolation, actually, you know, the one I was talking was, we have deltas. These deltas could be deltas of angular, and these delta thetas are, initially you have starting theta and you have final theta. The difference between the starting theta, and the final theta is delta theta. Delta theta is theta final minus theta starting. So this delta theta, if you divide it, divided by n, okay? If you divide it by n, number of partitions, okay? Number of partitions, then you get delta, smaller delta. This smaller delta, you know, maybe I could say it delta theta like this, you know, it is more closer to zero. It is more closer to zero. It's more closer to zero. So this delta theta, it is even equal to the precision of the motor. So for example, from the motor, you say the motor has a precision of 0.0 degree. Maybe that is, it may be equal to this one, you know. Actually, you could use even less, but the maximum, I mean, the maximum capacity of the machine is the maximum resolution, right? It cannot go beyond the resolution, right? So between the 2 points, yeah, it could go up to the resolution, but it is computationally costly because you have so many data in between, then it has to calculate the velocity in each intermediate points, and then it is a little bit computationally costly. But I could imagine this delta theta maximum to the number of resolution, but maybe lower for some applications, like for rough cutting, you know, for rough cutting where you don't need really high precision, or where you don't need really good surface finish, it could be lower, you know, you could divide into 100, you know. But if you need a good quality surface finish, you know, then you need to increase the delta theta into maybe 10,000, maybe 20,000, then you could have better results. But still, this is something where you could play, you know, it's you who has to decide, depending on the process. If your process really requires you to do so, then you have to do it. Otherwise, still you have to compromise between the speed or the performance of the machine and the process quality you desire. Yeah, but there is something important here when you decide about your deltas. When you decide about your delta, you have to think about chord error. What does this chord error? For example, here on this figure, you have a starting point here and you have a final point here. So your task is to make this pass plan, okay? For this pass, you know, if your theta, delta theta, okay, if this delta theta shouldn't comply to the chord error, then you will have some problem, okay? So I will tell you that. So in principle, the chord error, that, you know, from your mathematics, you know that this chord length, yeah, the chord length theta equals to SR, you know, some formula like this from old school, right? It is chord length divided by arc length divided by radius gives theta. So with this principle, so if this is chord arc length, you know, for this arc length is theta r. So this theta could be now delta theta times r. I don't know if you like, yeah, just to drive some mathematics. From this, you know, this is what we are talking here. From this, we can calculate the chord error. You know, the chord error, which was mentioned here, is, you know, between the arc lengths and then, you know, this line which connects the two arcs. The distance between these two is called chord error, okay? It's called chord error. That's where we formulate the representation. Now, the point is, if this chord error is large, you know, I don't know if how could you imagine. I will assume you have something like this. You have something like this. And now the distance between here and here, which is chord error, okay? Chord error is almost equal to what? Radius of the circle, right? It's almost equal to the radius of the circle. So if the chord length or chord error is higher, then it is almost half, it is almost radius, right? If it is smaller, then it is very small. So this principle actually works only for a chord error which is minimum as much as possible, okay? Which we call it even less than one. Otherwise, it doesn't bring a solution. So assuming this, okay, assuming this chord length is minimum, less than one, at least even less than 1 unit, then delta theta could be derived, and then you get something like this. You remember delta x was calculated by x start, x final minus x start divided by n. Then delta theta could be decided, okay, by making cos inverse of r minus 1 over r, which lets you to avoid, you know, larger chord error, okay? So which lets you to minimize the chord error while leading you to select a better result, okay? A better sample size. Now, if you have this delta theta, then from the delta theta, then you can calculate the number of n and so on by making the difference between these guys again. Okay, so saying all this, this is, yeah, the same thing with chord length equals to radius with arc length, degree, theta. This is theta equals to theta times r equals to arc length for very small segment, for the segment. Then finally, we come to the solution that we had talked last minutes, which is about the X and Y representation. If someone writes like this or this, has full right answer. If he writes something like this, also has full answer. Or if you write this also, you are right, you are right. Right. It's a way of cosine and sine interpretation, you know, nothing else. This is the one I show you. Xn equals to r cos theta s starting theta plus n delta theta. Yeah, this is when you expand this cosine theta plus n delta, then you get something like this. If you expand this again, you know, you get something like this. N plus 1 is, this guy is talking in future, this guy is talking at the current. And just they are talking at the starting point. That's the only difference with our formulation earlier was here. In our case, we had n minus 1 because we assumed theta s is at the origin. But here this time theta s is not at origin, so you have to consider the offset from origin to theta s. Nothing else. I mean, there's, you know, if you have some offset initially from the origin, then you need to have n. Or if it is on the origin, you start from n minus 1. Who was raising hand earlier?
Yeah, Professor.
Mm-hmm.
So, Professor, with respect to G course and M course programming, do we have to implement all these theta and theta values, or is just for explanation purpose? I'm just a bit confused about this implementation right now.
Yeah, so this is what is inside G02 or 03. Yeah, okay, so just to connect to our lecture, okay? This code, you know, when you ask the robot to do G02, the robot is performing this operation. You know, you get my point? G02 is a command which implements this formula. G02 or 03 actually. The difference is only the direction of theta. G01 implements this code. Okay, this is implementation of G01. Now, actually, what you know, just the point here is, if you have now, if you design a new NEC mission, you know, and if you write G01, it doesn't write anything, right? So you have to develop an algorithm which interprets this mathematics into G01 and G02. For example, okay, actually, I didn't share the code, but we have already implemented last year or before 2 years, actually 2 years ago, how to generate this with G01. Actually, this was generated. I will share the code for you just later on the model if you are interested, or maybe on GitHub. You know, just the point is, if we have to control a numerical control machine, then we have to implement this mathematics, you know, into the code. So in order to implement into the code, you know, G01, 02, 03 is actually a convention. It is a standard, but we need a method which prescribes this mathematics. So for that matter, we have to implement it into a function, maybe into a method in our programs, and then just run it. Yeah, that's first target. The second target just actually is you have to know actually the secret behind what is G01, what is 02. It's not only telling us someone G00 is a rapid positioning for something. 01 is something. No, just you have to able to explain what it is really behind, what is really behind. You know how the mathematics should work. So that is why we have to learn these things. And the other point is actually, yeah, there are so many assumptions, of course, behind. The assumptions behind are actually two things. One is we assume a constant distance, which we said delta, or delta x or delta y, or we assume a constant time between each segment. For example, we say each segment could be completed in 1 millisecond. Then that's a constant time. Or we could say each segment could be completed for 0.02 degree. Then this is a constant displacement. So in our assumptions, actually, we used only a constant displacement. And if you want to work on, if you want to check, okay, you can vary the you can vary a time actually. Just here our timestamp is 020402. Yeah, just here we have a constant delta x and a delta y. If you want to change with the time, just you can play with time and then you get something else. But what is again really interesting is maybe this question. You know, maybe you will understand a little bit better. Yeah, just for on exams, you know, just maybe you could be asked in different ways. But one is you will have a G code, something like this. And then you will be asked to calculate the distance at tens, for example, you know, at the tens iteration. So what you have to do is x10 equals to xs plus 10 delta x. Y equals to y of tens equals to ys plus tens times delta y, something like this. So now just if you look at this example, for example, you have a G code, which is G01, and you have absolute positioning, you have X and Y target positions, and then you have starting point and final point. This is starting point, this is final point. You have feed rate, which is speed actually here. The initial coordinates were given here. The acceleration and the decelerations are 5,000 counters per second square. And the trapezoidal velocity profile is used. Actually, the trapezoidal velocity profile allows you to linearly increase and move constant and linearly decrease. The triangular velocity profile lets you to linearly increase to the maximum speed and linearly decrease to the minimum speed, to the zero, of course, here. So now the guy just says we prefer the trapezoidal velocity profile, and then the machine starts slowly and reaches maximum and then decelerates. The minimum interpolation time is given as 0.002 seconds. So the machine, you know, has it has processing capabilities, right? So between 2 points, the machine has only a capacity up to 0.02 seconds, which is about 2 milliseconds. You know, you cannot achieve more than 2 milliseconds, you know. For example, you say you're, for example, in a robot, we have up to 50 frames per second, which is about 20 milliseconds. This is 2 milliseconds. Actually, this is very fast even, 2 milliseconds is very fast. But from a robot, we get only, a response only in 20 milliseconds, but this is more even fast. So the interpolation algorithm is set as follows. The first is you have delta x, which is the distance, the difference between the starting and the final point, which is 24 minus 5 is 19. Then this is the delta y, which is 32 minus 6, which is 26. Then you have Euclidean distance. Euclidean distance is the delta x square plus delta y square, which is 32. Then delta u is delta, okay? It is the feed rate times minimum time. It is a velocity actually. Velocity equals to f is velocity. Velocity is, I said earlier, if you remember, it is ds over dt. So we have distance, we have time, sorry, we have time, we have velocity. Velocity is 1000 count per second, and time is it is 2 milliseconds. So delta u is 1000 times 2 milliseconds, which is 2 count, it is 2 units. Then we have to calculate the number of samples. Possible number of samples is the Euclidean distance between the starting and the final point. We have starting point, you have end point. Between this, you have Euclidean distance L, which is 32. Now you want to divide this one into number of divisions. So it is 32 divided by delta u, which is the smallest distance, which is 2. So in total, you have about 60 points from the starting and the final. You have 60 points to be interpolated. Yeah, then this is actually how to divide, actually. How many points should be divided in the acceleration region, and how many points should have to be with the maximum velocity, and how many points should have to be inside the deceleration range, Now we say that we have to get, now we have 16 points between the starting and the final. Okay, we have 60 points. Now the point is the machine cannot accelerate throughout, right? Sometimes it will accelerate, then move constant, then it will decelerate. Now the point is how many of the points should be in the range of acceleration, how many of the points should be in the range of deceleration, no, constant speed, and how many of the range should have to be in the deceleration region. So this you could calculate by using this formula, speed, the square of the speed times twice of acceleration of delta u. Actually, this is nothing. It is, you get this one from acceleration, actually. From the acceleration. Acceleration means dv over dt. If you substitute everything like this, you get something like, for example, right? V square equals to v naught square plus 2 as, I don't know, from the physics. So this is physics. So maybe if you have initial 0, then final speed square equals to twice of acceleration times distance. Now you want to know actually the distance, because acceleration, the velocity, right? So distance equals to v square over 2s. But not only this, you want to know also number of, this distance has to also decide number of pointers. For this number of pointers, we know that n should have to be L over delta u. And then from that, you have to try out, different options. Maybe sometimes, in trapezoidal velocity profile, sometimes people say 1/3 of the sample should be to rising. Maybe 1/3 of the sample should be to deceleration. And maybe 1/3 of the data should have to be in the intermediate, with a maximum. Or sometimes, if your machine is capable, maybe you could accelerate fast, move maximum, and then decelerates fast, if that's capable. But as we have seen now, the machine is only capable to do feedback. It will give you only feedback only in 0.002 second, in 2 milliseconds. So you cannot go faster. You cannot command the machine to stop before 2 milliseconds. It's not possible. The maximum speed the minimum time you can communicate to the machine is 2 milliseconds. Okay, so in 2 milliseconds, stop, then the machine will start even to think about stopping after 2 milliseconds. It doesn't react immediately. So you have to think if this could really affect your process, because it could affect, right? If it doesn't stop where you want to stop it, then it is still a problem, right? So this is what you have to consider. But more or less you have an option to decide. But for this, actually, there is no, just there are lots of open spaces where you could think about and just reason out. Maybe you say, I just, for me, this is better, and for my process, this is not better or something. So just, just check and maybe read yourself. But as an overview, this is more than enough. That's one point. And if you want again still further, we have a video again still on this topic on the YouTube. Just you can listen to, you can watch the video from the YouTube, and maybe I will upload the code for this generation, and then you will see how it should work in Python, if you are interested in Python. Or if you want to understand more also how I implemented on my paper with MATLAB also, you can check the paper maybe. Actually, on the paper, what I did was, maybe just to give you some clue, I took any 3D model, which is in STL format, from any CAD model. Then I convert this CAD model into point clouds. From the point clouds, I try to generate a logic which identifies the part to be removed and the part that has to be retained. And then finally, I able to generate a G-code. Actually, I used, of course, existing libraries for G-code generation. And then finally, I tested. So from any 3D model, I able to generate a G-code from any 3D model using MATLAB scripts. So in such a situation, actually, what I did was, initially, I have to import the model into MATLAB in STL. And in point cloud as well, and then I have to convert into a bitmap image in order to simplify, because point clouds are too heavy for the MATLAB. So I have to convert into binary image where only part of the object and the part of the stock has to be matched, and then from that I will subtract the stock from the I will subtract the model from stock, and then I will get the part to be removed, as you see it here. Then finally, I will get the result. Maybe I could Maybe I could show you. Yeah, so now the concept is you want to make this object, right? You want to make this object. So by doing subtraction, then what I did was first I will define my stock, as you see it here. I will define my stock. From the stock, I will remove the inverted image of the part to be produced. You know, assume just this is a product you want, but from the stock, this black part, you know, in the middle should have to be removed. This is nothing. This is the inverted part of this image, and then I get these black pointers, and the black pointers should have to be generated into G code, so just like this. So this is not color, actually it is lines, you know, these multiple lines, just with a very precise distance. This is the logic actually I have implemented just in order to filter out. This is my tool simulation where I try to simulate the pass. Yeah, something like this. So yeah, it's also possible to implement these functions like that. Yeah, so this is all about for today's session, and maybe also, yeah, the last session, I think, for the semester. And yeah, just finally,